everything nice. And there is a slight Powerpuff Girl theme going through it. So if you don't like the Powerpuff Girls, just ignore it. You can ignore it, or you can get a bit involved. But yeah, I'm Grace, and I am a PhD student at the Open University, and I'm part of the Astrobiology group. So in my talk today, I'm going to be talking a little bit introduction to astrobiology, and then moving on to icy moons and why we study them. So I did my undergraduate degree at Edinburgh, and during that time mainly focused on the astrophysics part of the course, just because I really love space, as I'm sure a lot of you can relate to. And in my second year, I did an introductory astrobiology course, which kind of set me on the path that I'm on at the minute, doing astrobiology and icy moons. So hopefully I can share some of my enthusiasm for it today with you, and yeah, share my love of icy moons. So astrobiology is the official NASA definition, is the study of origin, evolution, distribution, and future of life in our universe. So this really asks questions like, where can we find life in our universe? Is there life elsewhere? And if there is, what would it look like? So the Earth is absolutely teeming with life, and yet we are only one tiny little rocky planet in a solar system that's a pretty small sun, and we are in a galaxy of over 250 billion stars. And here you can see this absolutely beautiful Hubble image of a globular cluster. So this is a collection of stars which are grouped together by their gravity. And this specific one is in the Scorpio constellation, and it's 35,000 light years away from Earth. And even though it's unlikely that there's going to be solar systems in this globular cluster which would host habitable planets, I thought it was quite a good image to kind of show a scale. Like every single little dot on this image is a star with its potential planetary system. So looking even wider into space, we're part of a universe that is host to at least 200 billion galaxies, each with their respective billions of solar systems. So the size of even our galaxy, the Milky Way, leads to questions about whether or not we are the only life forms in the universe. And this is something that has really inspired me moving forward. Like the size of space just absolutely baffles me. So our nearest neighbouring solar system is 4.5 light years away, but we can look to the astronomical bodies in our own solar system, so planets, moons, and even asteroids, and this can give us a lot of valuable information about how life managed to develop on Earth. So moving more into oceans, I've always been a really big blue planet fan, and absolutely love seeing all the crazy creatures in the ocean that is just here on Earth. So here what you're looking at is a female blanket octopus, and this, when it's in danger, when it senses danger, it unfurls this beautiful rainbow cape to ward off any predators. And this cape is up to 2 meters long. And the male of this species, so the female is 2 meters long, the male of this species is the size of a walnut, which I just find crazy. And I just think you see such a variety of life on our own Earth, in our own oceans. So if you look to an alien ocean, what could life there actually be like? So just to bring your expectations down a little bit, here you can see an image from the Perseverance rover, which is on Mars at the minute. When we're actually looking for life in our universe, we're not looking for octopi. I think that's how you say it. We're generally looking for signs of past life, like Perseverance is on Mars, or we're looking for even the teeniest, tiniest microbe that could give us evidence of life elsewhere. So in this talk, unfortunately, we're not going to be looking for any deep sea Enceladus creatures, but we're going to be looking more at like biomarkers. So biosignatures are chemicals which suggest signs of biological activity. And generally, when we're sending out space missions to look for life, this is what we're looking for. So to start building what we're looking for, we're back to the Powerpuff Girls. So you've got sugar, spice, and everything nice. But to find life elsewhere, we generally look for three things. So we absolutely think that we require liquid water. Almost everywhere that we find water on Earth, we find life. So water's presence or absence is an initial way to assess a planetary body's habitability. We also need to look for bioessential elements which we think are vital for life. So these are often called the CHNOPS elements, and this includes carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And these are really the building blocks of all the life that we see on Earth. And finally, we also need an energy source. So we need something that's going to give energy to these chemical reactions and actually catalyze the building of things like RNA, DNA, and then more complex molecules. So these are the three kind of essentials that we're looking for. And really what I'm going to concentrate on in this talk is water and where we can find it. So if we're looking within our own solar system, in the early days of astronomy and planetary science, the area around a star where liquid water is stable on the surface defines the habitable zone. So this is what you can see here. The green, the darker green is like the absolute, yeah, this is habitable. And then just a bit away from that is like, oh, maybe. So this is set by the distance from the star, where the inner boundary is where the solar luminosity is so hot that it sets in place a runaway greenhouse effect. And this is what we see on Venus. So on Venus, it potentially used to have liquid water, but this has all been boiled away because of how hot it is. And this limit happens at around 0.5 AU. So AU is astronomical units, and this is defined by the distance between the sun and the Earth. So 1 AU, or astronomical unit, is the distance between the sun and the Earth. So the inner limit of the habitable zone here happens at around 0.85 AU. Now, the outer limit to the habitable zone is set by the distance where the greenhouse effect is not sufficient enough to generate enough high enough temperatures to actually sustain the liquid water on the surface of the planet. And it's also where CO2 in the atmosphere starts to condense out, leading to greenhouse warming. So the outer limit of this is at 1.7 AU, so may actually include Mars. And although Mars may have once sustained liquid water on its surface, very much like Earth, it's had an insufficient atmosphere to kind of keep the planet warm enough and sustain that liquid water. So Mars is right in this maybe kind of boundary of the habitable zone. And we now know that it could potentially host subsurface lakes beneath its poles. And these were discovered by the Mars Express spacecraft using radar in 2018. But there's still a bit of ambiguity about that. More recently, researchers suggested that this could be clays instead of water. So Mars is kind of a maybe in the habitable zone. So from this, we can see we've only really got Earth in there. But this is quite a limited definition for habitability. It really depends on heating by the host star of the system. So firstly, life needs much more than just liquid water. A planet in the habitable zone could have enough liquid water, but may be lacking in some essential element. So for example, not having enough biologically available nitrogen. So even if a planet is in the habitable zone, it may not actually be habitable. And more relevant to this talk, planetary bodies may not have liquid water on the actual surface, but we now know that there are many bodies in our solar system which host subsurface oceans which may be habitable. Far out in the solar system, we get beyond the frost line, which you can see indicated here. And this is where water freezes out on the surface due to how far it is from the sun's nice cozy heat. In this region, tidal energy comes into effect. The more elliptical the orbit of a planetary body, the more the gravitational pull creates friction within the interior and generates heat. So instead of using the sun's energy to heat up a planet enough to sustain water, you can use the tidal energy of a body's eccentric orbit to generate heat in the interior of the moon, the planet, whatever. So this happens on Earth and is why we've got tides. So the planet is always like pulling and pushing and like really stretching out because of the gravity. And again, this causes a lot of heat. So this energy can help sustain liquid water on bodies which are way beyond this Goldilocks zone. So like not too hot, not too cold. It's habitable all the way out into the outer solar system. So if we look at the Jupiter system, we can get a really good example of how this new habitable zone can be formed. So here you've got an image taken by the Juno spacecraft, and you can see Jupiter, which is obviously the really big one, on the side, and then you've got Io closest to the planet and Europa just on the left. So Jupiter has 79 moons, and some of them are still awaiting naming, so around 24, I think, still awaiting naming. So it's got loads and loads of moons, but I'm going to concentrate here on some of the largest and most studied ones. So close to the planet, we have Io, and this serves as the kind of Venus in this tidal heating new habitable scenario. Because of the amount of heat generated by being constantly pulled through its orbit, Io is the most volcanically active body in our solar system. It has hundreds of volcanoes and lakes of molten silica on its surface, and its volcanoes are so powerful that they can actually be seen by large telescopes here on Earth. So this image is from Galileo showing an eruption on Io, and literally right this very minute, there's volcanoes exploding on the surface of Io. So Io, like Venus, has too much energy to maintain any liquid water. So on the outer end of this new habitable zone is Callisto, and this is the furthest out of Jupiter's largest moons. This is another Galileo image showing Callisto's surface. It's uniformly cratered, but not uniform in colour or brightness. So we think that the bright areas are mainly ice, and then the darker areas are highly eroded ice-poor material. So we do think that Callisto has an ocean, but it doesn't have enough tidal energy due to its eccentric orbit to keep the ice shell relatively thin. So any ocean on Callisto is trapped by this really thick old ice shell. And the ocean on Callisto has probably been sustained by, in the interior of the moon, there'll be radioactive elements that were got there during the formation of the satellite. And as they decay, they're going to release heat and then help sustain this ocean. But this is going to run out. And because it's so far away from Jupiter, the tidal energy is not generating enough heat to keep this sustained. So in this way, Callisto is kind of the Mars in this scenario. It was and maybe still is habitable, but the tidal energy is too small, resulting in it being colder and less active than the larger inner moons. So in between Io and Callisto, there's Europa and Ganymede, and they are pretty much in the sweet spot for maintaining an ocean. Both have icy shells, and Europa in particular has quite a thin ice shell, so from a few kilometers to a few like tens of kilometers, under which there is a liquid global ocean, which can be maintained due to tidal heating. Ganymede, however, is kind of a bit more like Callisto. It's got a really thick icy crust, and it may also have a seafloor layer of ice, which could prevent chemical nutrients from entering the moon's oceans from its rocky interior. So out of all of Jupiter's moons, the one that seems to have the most potential for life is Europa. Oh, this is a new habitable zone. So back to Powerpuff Girls. Blossom is the leader of the Powerpuff Girls. Europa is kind of like the star of the Icy Moons. So it's one of the most studied. We're sending more missions out there. So that is why there's a little blossom in the corner. So Europa is around 3,000 kilometers in diameter and is around the size of our own moon. And it's covered in ice. And here you can see what is known as the chaos terrain, because it looks pretty chaotic. And these are all the little stripes across the surface, which are thought to be caused by the tidal tug and pull of Jupiter. It has quite a young surface. There's not that much evidence of cratering. And planetary scientists usually use cratering as an indicator of how old or young a surface is. So not that many craters means that it's a pretty young surface. And you can see here as well, like there's all these cracks. It's quite geologically active. And if we zoom in on the surface a little bit more, you can see this beautiful image, which is a kind of product of grayscale data from one orbit of NASA's Galileo mission, and then this is combined with a lower resolution color data, which was taken on a separate orbit. And this whole image measures 163 by 167 kilometers. On here, you can see that there's some kind of blue-white terrains, and this is indicative of water ice. And then you've got these red regions where water ice has mixed with hydrated salts and potentially magnesium sulfate or sulfuric acid. Jupiter's huge magnetic field means that the surface is constantly being irradiated, and these constant bombardment by high energy particles are thought to weather the moon's surface and can drive chemical reactions and also alter the physical properties of the ice grain size. So if we go beneath the surface now, what really makes Europa so special is its ocean. Excuse me. So beneath the ice, there is a global ocean, which is it contains about 2 to 3 times the volume of Earth's oceans. So that's a whole lot of water for something that is the size of our moon. And what also is interesting about it is it's about 100 kilometers in depth. So a really thick ocean. And comparing this to Earth's oceans for like scale, Earth's oceans are generally on average around 4 kilometers deep, and at their deepest are around 11 kilometers. So on Europa, you've got this 100 kilometer deep global ocean. So 2 to 3 times the volume of water on Earth. And in contrast with Ganymede or Callisto, Europa's ocean is probably in direct contrast with warm rock on the seafloor. And if we look at the moon's interior now, we see that Europa has this metallic core made out of iron and nickel, and this is shown in grey in the middle. And then this is surrounded by a rock shell, shown in brown. And here you can see the ocean as well, so that's 100 kilometers deep, and in blue, and then the white bit on the edges is the icy shell. So the interaction between the salty liquid water ocean and the rocky interior could actually supply hydrogen and other chemicals to the ocean. So all this mixing can generate heat and new chemicals that go into the ocean. And while the energy for life on Earth comes directly from the sun, Europa's energy input might actually come from the surface chemistry and the water-rock interactions on the seafloor. So all this tidal heating has generated all this energy, created an ocean, and now we've got more chemicals being generated on the seafloor, which are potentially good for life. So it's also possible, and this is fairly new, that Europa's ocean is actually leaking out into space. And this hasn't actually been observed by Galileo on its flybys, but more recent observations from the Hubble Space Telescope and also reanalysis of some of the data from Galileo suggest that there are plumes of ocean material which are being ejected up to 160 kilometers into space. And here you can see a bit of an artist's impression of ocean material being ejected. So this is important because it means if we're sending a flyby mission out there, there is the potential to directly sample ocean material. And speaking of new missions that are going out, there are 2 missions that will be going to Europa very shortly. Here you can see a little kind of poster for Europa Clipper, and this is going to be launched in 2024, I think, and will directly study Europa with the main mission goal of searching for life. And there's also a European Space Agency mission called JUICE, which is going to be launched next year, hopefully. And this is going to go and study some of the icy moons around Jupiter. So focusing on Europa, Ganymede, and Callisto. So hopefully soon we'll get loads of new data to work with and a lot more kind of indication of whether these ocean worlds could be habitable or not. So when we're looking to icy ocean worlds, we're really looking for a planetary body which is right in the sweet spot for generating enough energy, but not too much from tidal forces. And we're looking for liquid water oceans beneath icy crusts, which are not too thick that they're unsustainable. And we're also looking for bioessential elements. So here I've put together a little graphic which shows some of the icy moons of our solar system. And you can see even as far out as Pluto, there's these potential for subsurface oceans. So Pluto's orbit is super, super elliptical. And we think that then now is potential for a subsurface ocean there. And if you think back to the start of the talk with that quite limited definition of habitability, only really Earth and Mars is included in that based on the sun's energy alone. Tidal energy can actually give us potentially habitable planetary bodies all the way out to the far reaches of our solar system. So both Neptune and Uranus have moons, which may suggest subsurface oceans, but only one spacecraft has been out to visit them, really, and that was in the 70s. So Miranda has signs of intense geological activity on the surface, and Triton is potentially hosting this subsurface ocean, but we've only had one spacecraft to really go through, and it wasn't able to get any magnetic field data. So personally, I think we should send some more spacecraft out there because yeah, it just like extends our limits of habitability, really. So now I'm going to move on to the Saturn system and for a more in-depth look at some of the most interesting moons in our solar system. So here is Titan, and this is an icy world whose surface is completely obscured by a golden hazy atmosphere. So Titan in the Powerpuff Girls is Buttercup, a little bit angry, covered in smog. There's lakes of liquid ethane and methane, and is a bit of a fighter. So the atmosphere is referred to as a Tholin haze, and this is where photochemistry reacts with this thick smog of nitrogen and methane and creates this kind of like thick atmosphere and obscures the surface of the moon from view at visible wavelengths. So Titan's also the only moon in the solar system with a dense atmosphere. All the others are airless bodies. And it is also the only world besides Earth that has standing bodies of liquid, including rivers, lakes, and seas on its surface. So this image may not look like much, but it shows the first flash of sunlight reflected off a hydrocarbon lake on Saturn's moon. So this northern hemisphere has been shrouded in darkness for 15 years, and the sun has reflected just right off it as it's come round in its orbit to capture this picture. And this was detected by the visual and infrared mapping spectrometer on board Cassini in 2009. So this image really confirmed the presence of liquid in the moon's northern hemisphere, and this is just off of a huge sea called Kraken Mare. Because Titan's atmosphere blocks out most visible light, FIMS took this image at infrared wavelengths to penetrate through the haze. So if we look at Titan using infrared, the surface is revealed. Here you can see flowing rivers of methane and ethane, which carves out river channels and fills these great lakes with liquid natural gas. No other world in our solar system, aside from Earth, has that kind of liquid activity on its surface. Gravity measurements from Cassini have also suggested that Titan could have a subsurface ocean, and this would be mainly liquid water mixed with salts and ammonia. Additionally, Titan's rivers and lakes may serve as a habitable environment on the moon's surface, but they're made out of methane and ethane, so any life there would look totally different to what it does on Earth. And again, we're going to go back and visit Titan, potentially as early as 2026. So this is a little video showing NASA's Dragonfly mission, and this is an 8-bladed rotorcraft which will take advantage of Titan's dense atmosphere to fly to different locations across the surface and sample material. It'll be the first vehicle ever to fly its entire science payload to new places for repeated and targeted access to surface materials. So its instrument suite is directly investigating the moon's atmosphere and surface properties, the subsurface ocean, liquid reservoirs, and areas where water and complex organic materials, key to life, once existed together for potentially tens of thousands of years. So, yeah. So we've seen two pretty different moons, Europa and Titan, and now I'm going to move on to Enceladus. And back to the Powerpuff Girls, Enceladus is kind of like the cute small one, so Bubbles. So it is my personal favourite because that is the moon that I'm studying for my PhD. And Enceladus is only 500 kilometres in diameter, so 504, I think it is. So it's roughly the size of France. But despite its small size, it shouldn't be underestimated because it's so geologically active. It's the smallest geologically active body that we know of in our solar system. So here you can see an image of its very young surface, which has been cracked and strained due to the tidal forces, quite similar to what's happening on Europa. What makes it so fascinating, however, is in the South Polar region, there are these huge cracks in the surface known as tiger stripes. And these are around 130 kilometres long, 2 kilometres across, and 500 metres deep. The tiger stripes are host to up to 100 jets, which vent out icy material from the ocean thousands of kilometres into space. So this is an image taken by Cassini again during a flyby event. And the discovery of these plumes was so exciting that the entire Cassini mission got rerouted just to fly by past Enceladus. And while they did that, they got a little taste of the plume material. So this plume material has been sampled, but because the spacecraft flew through at such high speeds and it's being ejected at such high speeds, a lot of the material, so heavier molecules, got fragmented when it impacted with the detectors. But from this analysis, we can see the presence of molecular hydrogen. And this is important because it suggests that deep in the planet's in the satellite's interior, there's hydrothermal activity taking place. So on Earth, hydrothermal activity is one of potentially the most likely places where life originated. And on Earth, it's, like these hydrothermal vent systems are host to like very diverse biological communities. So detecting molecular hydrogen in these plumes was a pretty big deal. The plumes which get ejected from Enceladus also go on to feed Saturn's E-ring, and this is the second outermost planetary ring of Saturn, made up of microscopic icy grains and silicates. And this is another key thing. So the presence of silicates in these grains also points to hydrothermal activity. So there's a whole host of evidence that's being built up to show that this is what's happening on this satellite. So within the rocky interior of Enceladus, the rock is interacting with the ocean and then leaching out these silicate materials, which then get transported all the way through the ocean, through the icy crust, into the tiger stripes, and then ejected out into space, falling into orbit around Saturn. So my work really focuses on Enceladus's ice surface and what we could potentially learn from it. So moving on, we can see the interior structure of the moon, from the rocky interior to the ice shell and the plumes. So the majority of plume material actually goes on to fall back onto the surface. So around 99% of this material is giving Enceladus a global dusting of like potential ocean material. The rest of the plume material goes on to feed Saturn's E-ring. And as Enceladus orbits within this structure, this can kind of recycle plume material through the E-ring and then get redeposited back onto the surface. Again, what else is happening on the surface? Similar to Jupiter, Saturn has a magnetosphere. So Saturn's magnetosphere is a lot less intense than Jupiter's. So it's a less intense radiation environment, but that doesn't mean that nothing's happening. So we've still got these high energy particles which are impacting the surface And again, like Europa, potentially driving chemical reactions, species creation, and altering the physical properties of the ice grains. So why can we not just sample the plumes or directly sample the ocean? And this is something which is similar to Europa. So the ice is expected to be thinnest in the South Polar region, where it's around 5 kilometers thick. However, even on Earth, the technology doesn't yet exist to drill through ice this thick. So it means that it's unlikely that on one of Saturn's moons, we're going to get the technology to go through, penetrate through, and get to the ice crust. The Europa Clipper mission is going to, after that goes off, there's the concept mission for Europa Lander, and they're going to be scooping up icy material on Europa. But even then, even if they do get a little scoop of ice, it's going to only penetrate down to 5 centimeters. So not very deep. So again, if we look at the surface, unlike the Cassini mission, you've got a stationary target. So you haven't got the plume grains flying out and impacting these detectors really fast, fragmenting grains. You can target locations of interest. So if you want to go to the South Pole, you can target your spacecraft to land there. You've got stationary material to sample. And as well as that, you've got all the magnetosphere interaction, you've got the E-ring grains being deposited. So looking at the surface can give us a really good idea about both what's happening beneath the ice in the ocean and what's happening in the space environment. So this leads on to what I do in my PhD. And the main aim of what I do is kind of thinking about how we build an icy moon in the lab. And I am developing a system which is capable of replicating surface conditions. And then I'm growing analog Enceladus ices, which can be then analysed, and you can do experiments on them. So if we're replicating these surface conditions, we want to have 3 things, really. So Enceladus is an airless body, so we need high vacuum conditions. And in the lab, this means using a vacuum chamber with a fairly intense vacuum pump to suck out all the air. Temperatures around the South Pole are at around minus 95 degrees Celsius. So if we're specifically looking at Enceladus, the South Pole is minus 95 degrees Celsius, and then the rest of the satellite is around minus 120. But as this is the region most of interest, we're getting down to minus 95. So this means using liquid nitrogen. And then lastly, we need to get some ice. So this is what I've been working on, growing ice in a system in the lab. So this is a picture of my current equipment setup, which I have built. And this is the vacuum chamber that I'm using. You can see it's that little grey shiny chamber, and it has a 35 litre capacity. And inside it, you've got a little sample holder where you can grow ices. So here you've got the vacuum chamber. On the side, you've got some of the control systems. And then right at the top there, you can see, which is like the little cross, you can see a mass spectrometer, which is being used to analyse the ices. So the Enceladus ice is predominantly water ice, with evidence for CO2, methane, ammonia, and salts. And over the past year, I've been working on building this system in which to grow the analogues and really refining the protocols to grow the ices. So currently what I do is I put liquid water or brines into the sample holder and then freeze them down using the liquid nitrogen, so get everything nice and cold, and then get all the air out the chamber, so evacuate the vacuum chamber, get it down to pressures of about minus 10 to the minus 6 millibar, and then I start injecting gases onto the sample. So this builds up these little layers of ices. And then I am going to analyse them, get together some pristine ice compositions that would be like, okay, this is what the pristine ice would look like before any space weathering. So at the minute, I'm working on the initial analysis, and later on, I'll be doing some space weathering experiments. And this is in order to build up a catalogue of potential ice compositions. So this initial analysis of the ices is used as a comparison for future experiments, and this will be using impact experiments using the light gas gun at the Open University, which you can see here. And this is really to replicate E-ring grains impacting the surface. And I will be firing silica projectiles at my pristine ices and then reanalyzing them in order to compare. So here you can see the little chamber where the target ice samples get placed, and then right away in the background you have the projectiles which are fired from here. So this is pretty much the next stage of my PhD. I'm still working with the ices, and then I'll be working on mating the system that I've built to the light gas gun in order to get these space weathering experiments done, building up this catalogue of potential ice compositions. So that was a bit of a whirlwind overview of my work, and I'm going to leave it there. So just coming back round, hopefully I've been able to show you that our old definition of habitability is quite limited. There are all these moons and planetary bodies in our solar system which are really worth studying because they potentially have subsurface oceans where we could look for life. So hopefully you've had a good time looking at some beautiful space pictures and learning about the space missions. Yeah, I'm going to leave that there and leave you with this image of Enceladus because it's my favourite. And I look forward to hearing any questions.
Thank you, Grace. That was really, really great. And there's a few moments I was looking at some of these photos and I'm like, oh my gosh, wow. And you're saying all this stuff. And I'm like, oh God, brilliant. Do you want to unshare your screen? And then what we'll do, I will stop the recording and then we'll go into the question.